This is a Crookes radiometer. You can see there is a vein, or 4 veins in the middle, perhaps you can call them paddles, that are being pushed around. This glass vessel contains a very low pressure gas, maybe it's air, doesn't really matter, a very low pressure gas. And the veins in the middle spin around when this is exposed to light. But the question is, how does this work? Now, there are 3 explanations that have been given historically. The first explanation, the oldest explanation, was that light carries momentum. And that is true, light does carry momentum. But the explanation goes that light carries momentum. When the light is incident upon the dark side of the veins, it's absorbed, transferring its momentum to the vein. But when light is incident upon the shiny side, it's not absorbed, it's reflected, transferring twice as much momentum to the vein. Obviously, rate of change of momentum is force, so that causes a force to be exerted upon the veins. Now, if that theory is correct, the shiny side would feel a greater push force than the dark side. And so you'd expect the vein to spin the other way round. So whilst it's true that light carries momentum, that cannot be an explanation for how the Crookes radiometer works. The second explanation was that there is slightly warmer gas, slightly higher temperature gas around the dark face than the shiny face, because the dark face is a better radiator of electromagnetic radiation, of infrared radiation. So the idea that because the gas on one side of the vein was slightly higher temperature than the other, the gas particles on one side of the vein would be moving slightly faster than the other. And thus, when they collide, through random chance, when they collide with the veins, those gas particles traveling at a higher speed would transfer more momentum. So the dark face would feel a greater push force than the shiny face. Well, that would certainly explain why it spins around this way. The problem with that explanation is that you also have the gas expanding in all directions near the dark face. So whilst that does mean there's going to be particles moving faster towards the vein, it also means there's going to be particles moving away from the vein. And they are going to collide with other air particles, reducing the amount of air that can reach the vein in the first place. Now, that explanation and then that counter to that explanation have been discussed lots of times throughout history. Someone cleverer than I am calculated that actually the 2 effects will cancel out, so there'll be no net force on the vein. So then someone even cleverer than that, Albert Einstein, did some calculations and said that that is true, except at the edges. At the edges, there would still be a net force on the veins, pushing it around in the direction it goes, but it wouldn't be enough force to get the acceleration of the veins, or to get the speed of the veins, because of course we've got resultant force on these paddles of ultimately 0 due to friction where the paddles are connected to the orb. Anyway, I digress. Oh, Einstein proved there wasn't enough force. So, the third method, which is called transpiration, that happens in porous substances. If you've got a porous substance, on the dark side, the gas is going to be at a higher temperature than on the light side, or the shiny side. And because it's porous, the gas can move through it. So the gas will tend to move through it in a particular direction, from the hot side to the cold side. Okay, fine. Does that explain this phenomenon? Well, not really, because these metal veins are not porous. Someone cleverer than me, can't remember his name, I think it was Oswald or something, can't remember, showed that actually at the edges it behaves a bit like a porous substance. Tricky thing to explain how it works. I've probably not done a very good job of it. So have a look, if you're interested, at the Crookes radiometer and the history of the explanations of how the Crookes radiometer works. It's a fascinating instrument, a toy really, invented by someone investigating low pressure gases.